Welcome to MyProjectBazaar.com.
Now we discuss about the product for an implantable versatile electrode-driving ASIC for chronic epidural stimulation in rats. Next we see the abstract for the product. In spinal cord injured individuals, the neural pathway between the brain and the extremistic is damaged to some extent, paralyzing the lower extremities. Recent advances in the field of neuroscience have suggested that epidural spinal cord stimulation can facilitate recovery the bladder function, standing and perhaps locomotion in SCA human. Some rat studies have supported this concept, but further testing is required to increase our understanding and optimizing the stimulation parameter. Testing protocols are currently limited by the available technology. More especially, the number of electrodes one can use seriously limit the paradigm that could be investigated. For this reason, electrode array as opposed to conventional pairs of electrode can be used to investigate the effect of ESCS at different sites. The development of epidural electrode array for chronic testing in rats is a challenging task due to their small size. The difficulties increase radically when the larger number of electrodes need to be independently controlled. It has been well documented in the literature that the large number of connections is highly undesirable because it either makes the implantation procedure more challenging, or if the device is successfully placed in the body, it could imperil precision, result in infection, tissue damage, or simply cause the device to fail. This paper presents the design of testing an electrode-driving application-specific integrated circuits intended for epidural spinal cord electrical stimulation in rats. The ASIC can deliver up to 1 mA fully programmable monophasic or biphasic stimulus current pulses to 13 electrodes selected in any possible configuration. It also supports interleaved stimulation. Communication is achieved via only 3 wires. The current sources and the control of the stimulation timing were kept off-chip to reduce the heat dissipation close to the spinal cord. The ASIC was designed in a 0.18 micrometer high voltage CMOS process. Its output voltage compliance can be up to 25 volt. It features small core area. It consumes maximum 114 microwatts during the full stimulation cycle. The layout of the ASIC was developed to be suitable for integration on the epidural electrode array, and two different versions were fabricated and electrically tested. Results from both versions were almost indistinguishable. The performance of the system was verified with different loads and simulation parameters. Next we see the flow diagram for the product. This is the overall flow diagram for spinal cord injury operations. This is the voltage input and the power and reset function. This reset function to be controlled by the data demodulation block. Voltage input is to analyze the carrier based signal and to demodulate our final output data bits. This demodulated output data bits to apply to the shift register function, and to create the clocking function to apply the shift register controlled architecture. These two functions to be controlled by the controlling block. The reset controlled block function to be analyze the overall sequence and to generate the counting operations. Then the counting operation to be created for the mode selection control logic, and the power and reset to be applied by directly. These controlled function to generate the data bits and to process the mode selection logic, and controlled by the serial in parallel shift register function and parallel in serial shift register. The serial in parallel shifted by the data bits one by one, and the parallel at the same time process wise parallelly shift for all the data bits simultaneously. These the two function controlled by the mood selection control logic. This control logic controlled by the day by day manner, and the another process to be passed in the output stage block array. This stage block array to analyze the reference current and the control selection logic. The reference current selection is to set the threshold function level and to apply the control selection logical operation. Control selection logical operation to create the output stage output data bits for each and every electrode output pins. The electrode output pins to be consist of the hobbies to maintain the all the signals and to analyze and to apply the final output data bits. These data bits to be presented in the electrode signal. The electrode signal to be consisted by one by one. The array of array process to be count the 13 array process to be presented, and the final output 13 electrode pins output to be finally get the our overall architecture process. Then to final graph and result power calculation also presented in our overall architecture. This is the final flow diagram for process. This is our final output for the product. This is the final design. This design consists of the demodulation block and the parallel input, serial input parallel out shift register, parallel input parallel out shift register, and the current switching voltage reference based current switching block of find the electrode data output block. These blocks are defined by the 13 electrodes function to be array formed structure to be presented in our overall design. The 13 result to be passed in the level of parallelly and to analyze the overall database to represent the our design environment. This the design, and these designs are developed by the based on the CMOS based switching concepts. These switch to be length by the 0.25 micrometer square. This CMOS operation to be consist of the PMOS and NMOS combination to be presented in overall architecture, and active and passive devices to be completed for our overall architecture design purpose. Then all the design to be placed in our required schematic idiomatic designs. This design to generate the output result and to output result to be presented in this type of manner. This manner to be represents the example of 3 electrode signal 1 by level by 11, and this is the shift register output and the V input and the clocked output. The demodulation block to be applied by the voltage input and the power on reset condition, and to generate the shifter register block and the clock, and to passing the serial to parallel conversion and parallel input to parallel shift registering operation to be shifted by one by one level. Each level to be represented by the current based switching conditions, and to generate the electrode output block for our overall final output design. This is the output for the final product.